Okay, so welcome back. So this is just a short video going through the answers to the exam questions at the end of the entropy pack. I've had a few technical problems, so I've already written out the answers and I'm just going to go through them with you. Okay, so this is going to be quite a long video, so please feel free to kind of forward to the bits that you got stuck on or where you got some questions wrong, and do remember that you can still email us. So if there's any questions that you're still not sure on about why the answer is what it is, do drop us an email. Thanks. Okay, so we're on the first of the multiple choice questions. So the first one asks us which of the following is true for an exothermic reaction. So if we have an exothermic reaction, we know that my delta H value is going to be negative. We therefore know that the delta S surroundings term is going to be positive because that's minus delta H over T. And we know that my delta S system is going to be positive. We know that because I'm going from solids and an aqueous to aqueous and a gas. So because this is a gas here, it's going to increase the entropy of the system. We know that when we put those two things together, we add our surroundings to our system to get our total. Well, both of these numbers are going to be positive, so therefore my delta S total will also have to be positive. So those are things we know. Then what we're going to do is match those across with our answers. Well, delta S positive? No, it's not. It's negative. Surroundings is positive? Yes, it is. System is negative? No, it's not. It's positive. And delta S total is negative? No, it's not. It's positive. So the only correct answer there is B. Okay, on to the next question. When ammonium nitrate crystals dissolve in water, the entropy of the system does what? Well, we know it's going to increase. Okay, so that narrows it down to two answers. Now, the problem here is C rises because the ions become more hydrated. That is true, but it's not an explanation as what happens to the entropy of the system. So it rises because the ions become more randomly arranged, and that is a good explanation of the entropy of the system. Okay, so we're now on to the calculation at the bottom of this page. The thing we're going to be very, very careful with in this one is units. Do remember that enthalpy is given in kilojoules per mole. Entropy is in joules per Kelvin per mole. Delta G, on the other hand, is back in kilojoules per mole. So the first thing I'm going to do is I'm going to write my expression, delta G equals delta H minus T delta S. And this is all determined by the system because we've got rid of any nasty surroundings terms. So I can work out my delta S system. That's going to be 2 lots of my ammonia. Take away my nitrogen and 3 lots of hydrogen. So I'm going to get my value here of minus 199. Now this is in joules per mole per Kelvin, so I need to convert it into kilojoules, and I do that by dividing by 1000. Now what I'm going to do is I'm going to put that delta G value, to work out my delta G value, I'm going to put my numbers in. So that's my delta H value minus this term, which is my temperature times my delta S, my system, and it comes out as minus 32.7 kilojoules per mole to 3 sig figs. I'm giving my answer to 3 sig figs because all of my data here is given to 3 sig figs, so that's an appropriate number. The last step, I've been asked to show that this reaction is feasible. So I need that statement at the end. Delta G is negative, therefore the reaction is feasible. This is again a step quite a lot of students miss out. It's not enough just to calculate delta G on its own. You need to say how you know that it's feasible. And it's feasible because you worked out the delta G. So we'll be asked to explain in terms of entropy why this reaction is not feasible at very high temperatures. So again, we're going to look at my delta G. So delta G equals delta H minus T times delta S. Now at very high temperatures, this minus T times delta S term becomes a large positive number. Because remember, my delta S was negative, so when I times a negative by a negative, it becomes positive. Eventually, if this temperature gets high enough, it's going to outweigh this negative delta H term. So if this becomes such a large positive that it becomes larger than this is negative, therefore the delta G will become positive. So eventually delta G will become positive and the reaction is therefore not feasible. Okay, so next question, we're on to question 4. And we're asked to explain why the entropy of NO2 gas is greater than that of BaO solid. And this is a very, very straightforward question. It's basically, well, one's a gas and one's a solid. Gases have higher entropy than solids, so therefore it has a higher entropy. The next question, a little bit more complex, and it is down to complexity. So barium nitrate is more complex than this barium oxide. If you like, it's got more things in it that I can rearrange. It's got more energy levels that I can play around with. So it's a more complex compound, and therefore it has a greater number of arrangements and therefore higher entropy. Last question on this page was asking us to calculate the delta S of the system for this reaction, again with signs and units in my answer. So basically I'm just calculating my delta S system, which is where I end up, take away where I started from, and I get plus 439.1 joules per mole per Kelvin. Don't forget the sign, don't forget the units. Little bit of a double check, it's a positive value. Does that make sense? Well, yes it does, because I'm going from 1 mole of solid to 3 moles of products and 2.5 moles of gases. So I'm expecting this value to be positive. Okay, so top of the next page, I've been asked to calculate the delta S surroundings for a reaction and to include, again, signs and units. So again, I'm writing out my expression. Delta S surroundings is equal to minus delta H over T. This time it's an endothermic reaction, so that's a positive sign here. Don't forget to times by 1,000 to change it into joules per mole rather than kilojoules per mole. Divide by the temperature, 298 Kelvin. So I get an overall negative value, and I've just given my answer here to 3 sig figs. Okay. So the next question looks at the delta S total, and the delta S total is simply the sum of the two parts, so system plus surroundings, and we get an overall negative value. Now the second part of this, explain the significance of this sign. Well, because it's negative, therefore the reaction is not feasible, and that's the second part of my answer. Delta S total is negative, therefore the reaction is not feasible. Okay. Last bit of this is to calculate the minimum temperature at which this reaction occurs. Now, delta S total is equal to the system plus the surroundings. Remember, this is my surroundings term. Now, the minimum temperature at which this reaction becomes feasible is where delta S total is equal to 0. Because if I move any direction from here, I'll either become feasible or non-feasible. So you can say this is the tipping point, the point at which it changes from being feasible to non-feasible or vice versa. So I'm going to set that to be 0. Then what I'm going to do is I'm going to rearrange this equation. So I'm going to take this minus delta HT term over to this side and it becomes positive. So I've got delta S system is equal to delta H divided by T. I'm going to cross multiply, so this T is coming up. The system is going down, and I get my term here, T equals delta H divided by delta S system. You don't need to show all of that, okay? All you're asked to do is calculate it. So basically, you just need that expression there. Now what I'm going to do is put my values in. Doesn't matter whether I change this value on the bottom into kilojoules or I change this value on the top into joules, but I've got to do one or the other. In this case, I've times this top value by 1,000 to change it into joules. And then I've got my answer of 1,150 Kelvin. In other words, I'd have to heat this above this value to make it feasible. So this is the minimum temperature at which it will decompose. Okay, so we're on to question 5. And this is asking about the thermal decomposition of calcium carbonate. And we're asked to show by calculation that this decomposition is not feasible at 298 Kelvin and calculate the minimum temperature at which it does decompose. So the first thing we're going to do is we're going to write down our expression for delta G, and delta G is delta H minus T delta S. So we have our delta H value and we have our delta S value, so we're basically just going to put those into our expression and we're going to calculate them. We're going to be careful to remember to change this term here into kilojoules, because everything else is in kilojoules and we want our answer to be in kilojoules per mole. So when we do that in our calculator, we should get plus 129 kilojoules per mole. We're asked to show that this reaction is not feasible, so we do need to show that. We need that little statement in there. Delta G is positive, therefore the reaction is not feasible. That's why we know the reaction is not going to work, or the decomposition is not going to work. We're asked to work out the temperature at which it becomes feasible, and this is exactly the same calculation as we've done on the previous page. So this time it's delta G we're setting as 0, but we've still got the same expression here. So the temperature at which this reaction becomes feasible is expressed by this reaction, by this equation, is delta H divided by delta S system. So again, making sure things are in the same units. So in this case, I've changed everything into kilojoules. So I've got 178 kilojoules on the top, and I've got 165 divided by 1,000 to change that into kilojoules on the bottom. And I do that calculation, I get 1080 Kelvin. In other words, I have to raise the temperature of my calcium carbonate above this value for it to become feasible. In other words, for it to start to work. And you know that because you've done that in your group 2 notes, where you did the thermal decomposition of calcium carbonate, and you had to heat it quite strongly in the Bunsen burner to get it to decompose. Okay. Next question on that page. We're looking at the differences between these three entropy values. Very similar to a question we did on the previous page. We're looking at two solids and a gas. Well, the gas has the highest entropy because it's a gas, and of the two solids, the zinc carbonate is a more complex compound than zinc oxide, so it has the higher entropy. So usually we look at state first, then we look at temperature, then we look at complexity. Temperature is irrelevant in this case because all three are measured at the same temperature, in other words 298 Kelvin. So we're just considering state and complexity. Okay, so nice simple answer there. CO2 is the highest because it's a gas, and gases have higher entropies than solids. And then zinc carbonate is more complex than zinc oxide. That's why it has a higher entropy. Okay, so the last bit of our notes, we are looking at the entropy change for the system. And again, we're reminded that we need signs and units in our answers. So my delta S system is very simply where I end up, take away where I started from, and I get a value of plus 174.8 joules per mole per Kelvin. Again, I get 1 mark for working out the value. I get the other mark for the sign and the units. I'm then going to move on to work out my entropy change of my surroundings. Well, surroundings is minus delta H over T, and this is an endothermic reaction. So I've got a positive value there. So overall, this is a negative term. I'm going to remember that I need to convert this into joules by timesing by 1,000 here. And I get my value as being minus 238.3. I could change that to minus 238, give my answer 3 sig figs, but I'm going to use it in the next question, so I'm going to leave it like that for the moment. So the next question, I'm asked to calculate the total entropy change for this reaction, and that's very straightforward. All I'm going to do is I'm going to add my system and my surroundings together, and overall I get a negative value. So that negative value tells me the reaction is not feasible at 298 Kelvin. Okay. Now, the next question, what does the result of your calculation indicate about the natural direction? Well, as the delta S total is negative, the forwards reaction is not feasible. So we know it's not going to work in the forwards direction. But if it's not feasible in the forwards direction, that implies that it is feasible in the reverse direction. So the natural direction is backwards. Okay, because if I was to work out the delta S total for the reverse reaction, the magnitude of this value will be the same. It'd still be 63.5, but it will be positive. So the only thing that would change about the reverse direction is the sign. So the natural direction, the direction the reaction wants to go in, would be the backwards or the reverse reaction.